Good afternoon, everyone. Welcome back to E304. This is Elena Viti, and today we're going to be talking about nanomechanics. So this is the discussion or explanation of forces that move things at the nanoscale. So it turns out that both classical and quantum mechanics are very useful in this discussion. So we'll go over both in the next few lectures. So classical mechanics is very useful in predicting the motion of classical objects, but there are some issues or question marks that classical mechanics can't answer properly. So classical mechanics let's call them shortfalls. And we talked about most of these in the past chapter. So there's three main ones. First of all, classical mechanics is not good at explaining for us why fundamental physical qualities such as energy of an atom only assume specific values. So this concept of why things are quantized, why only certain energies are allowed, those sorts of concepts. Again, why some objects like electrons and photons act like both waves and particles. So the whole wave-particle duality is one issue. And finally, the uncertainty principle, or the fact that we can't know about an object's exact momentum and its exact position at the same time. So we talked about these in the last chapter in detail, but I just thought I would bring them up again. So again, we're going to talk about both classical and quantum mechanics, and really the thing that's most relevant to nano is related to oscillations and vibrations. So when we're talking about things at the nanoscale, we're talking about atoms, we're talking about molecules and particles, and we know that these things vibrate and oscillate all the time, and that these atomic atom-to-atom and motion and forces are really what we're going to be focusing on when we speak about nanomechanics. So let's start with a really quick reminder or overview of motion. And this is going to be quite useful for us moving forward. So let's remember, and perhaps some of these are still familiar for us. If we're talking about the motion of an object, we can speak of its displacement. So let's assume this object is moving in the x direction, delta x. We know that its displacement is the final x, final location, minus its initial. Okay, and this displacement is usually given in, say, meters. If we're talking about the displacement of an object, the next logical place to go is its velocity. So the velocity, we might remember, is the displacement over time. And then the next logical step from that is acceleration. And acceleration, we might remember, is change in velocity over time. So velocity is change in displacement, acceleration is change in velocity. Well, if we take these three primary equations, we can derive some more useful equations of motion. So let's look at this one and this one individually. So let's start here. Let's say delta V is equal to A times delta t. So all I've done is moved the delta t to the other side of the equation. Well, if we take the integral of both sides on this equation, we can find that velocity is equal to a times t acceleration times time, and plus, of course, the initial velocity v naught. Okay? If we then go and look at the dx dt equation, we can do the same thing. We can say that delta x is equal to v times delta t. If we take the integral of both sides of that equation, substituting our equation for v over here, we end up with at, so the integral of at plus v naught dt. Okay, so from that we can say that x is equal to, if we take the integral there, that gives us at squared over 2 plus v naught t plus x naught. Okay, so if we take these two equations and combine them further, so I have one equation here and one equation here. If we take these two equations and combine them further, we can come up with a couple of more useful equations of motion, and I encourage you guys to write these out and derive them on your own paper and your own notebook, and I think it's a useful exercise. So we can combine these and come to the conclusion that x is equal to x naught plus 1/2 v plus v naught times t. And the other useful way to express this is v squared is equal to v naught squared plus 2a x minus x naught. Okay, so these four equations of motion are very useful to keep in mind. Okay, so to look at these in a visual sense, let's look at displacement, velocity, and acceleration in graphical format. Let's draw a graph of displacement with respect to time for some object, time in seconds, displacement in meters, and let's say that this function looks something like this, something squared. And then let's look at the velocity of the same object, velocity in meters per second, time in seconds. Well, we know that the velocity is the derivative of this displacement function, so it's going to be a line with a constant slope, so a straight line, if you will. And then if we look at the acceleration, we'll see that the acceleration, of course, is the derivative of the velocity, and of course that's going to be a constant value. If I can see if I can draw a better straight line here. A constant value. And of course, for these equations that we've derived in the past slide, acceleration is considered to be a constant value. Okay, so the next thing that we should remember, and this comes from Isaac Newton and his laws, we can say that the sum of forces, this is the second Newton's second law, sum of forces is equal to mass times acceleration. And force, of course, is given in newtons, and 1 newton is equal to 1 kilogram meters per second squared. Okay, so the motion equations and this force equation are going to be useful for us moving forward. So where does this bring us? Well, it brings us to a discussion of vibrations and of motion at sort of the nanoscale. And we're going to talk about springs, and beams. So it turns out that oscillatory motion is common to all matter, specifically atoms, and a good model to use to sort of visualize the forces on these things is a ball on a string model. So let's assume that we have a wall here, if you will, and then a spring. I'm going to do my best to draw what looks like a spring here, and some mass, some ball of a given mass attached to the end of the spring. Okay, and we may or may not remember that the force on the spring, F spring, is equal to minus kx, and of course it's a force, so it's also equals to mass times acceleration, where k here is the stiffness of the spring. Okay, so this model, this ball and spring model, is very useful for us because it turns out that it can explain how cantilevers work, or beams. So let's assume we have a beam that's attached at one end to some surface, and this beam bends, or it can be deflected or pushed one way or the other. All right, so that works. That can be explained by this ball and spring model. Also, if you have two atoms, so let me draw two nuclei with the orbitals and the electrons floating around. So if you have two atoms, the forces between those atoms can be explained by the same sort of concept, where now you have two balls that are connected by a spring. So we're going to use this ball and spring model in the next lecture to understand a little bit better about how these interactions at the atomic level occur.